Welcome back, everybody. Well, it looks like I only scared away one third of you. Now you're back. It's okay. All right. Well, let us continue. Just a couple of quick announcements. I always start off with some announcements to make sure that everybody's on the same page. I uploaded a couple announcements for you. You may want to take a look at them. Pretty. It's one is a YouTube video of a crazy scientist that really does. The British scientist. He does a very good job of explaining a lot of stuff. So take a few minutes just to view it, and you might enjoy it. The other announcement I sent was a file which deals with metric units, because next chapter we'll be talking about converting from units from English to metric units. And one of the challenges that people have are things like millimeters, liters, centimeters, decimeters, and I try to put it all out in the table, and you can see the relationship between mass and volume and length with respect to the metric units. Okay, so take some time and view those when you get a chance. Let's see. That's all I have. Let me make sure I got more people coming in. Okay, we're moving up there. Um, Continue with assignments. Like I stated, I sent an email concerning the labs. The labs are designed to be on your time. So there's a lot of self-study really that you really have to kind of invest to get in there. Like I stated, it may vary from 2 to 4 hours is the average time length. So allot yourself plenty of time if you can to get those labs looked at, and it will may involve going ahead in the lecture part to kind of get an idea of how to answer the questions. Now the questions, hopefully they're not too complicated. I mean, in other words, you can probably figure them out yourself with not much of a problem. But if there is, shoot me an email. You can get out of the lab and you won't lose your spot. You can go back in it again. Shoot me an email and I'll get back to you with any questions, and I'll get back to you as soon as possible. Okay. So, so far, anybody have any questions? Everybody knows where to get their assignments, where to get files, where to get everything they need for this class, right? No surprises like a week before finals, right? Okay. Just making sure. Okay, well, I will got a couple more. All right. I guess I didn't scare away too many. Only a couple. Okay, well, let's go back to the chapter that we ended. We ended up on slide, I believe, 15. We were talking about physical and chemical properties. Now, this first chapter um, normally used to be that we would get into the mathematics of it, and I kind of give you a review of mathematics, and it kind of just blew a lot of people away. So we kind of changed it up a little bit. So let's talk about a little bit about chemistry. We'll get back to the actual aspects about the physical and chemical properties, but kind of introduce you to the chemistry. Then we jump into the mathematics, okay? And only because we will be doing calculations with respect to chemical equations. We'll be able to look at an equation, actually determine the products of the equation. Actually, let me take it a step further back. We'll start off with the elements. We'll start off with the atoms, all the different elements. From there, these elements, we will build compounds, okay? And so think of it as the elements being our alphabet. And we're going to take that alphabet and create letters and words. And then we're going to start adding these words together to create sentences. So we're taking the elements, making compounds, and taking compounds reacting with each other with other compounds to create products. And those products, obviously have the elements involved with them. We'll figure out what those products are. Once we figure out the chemical reaction and the chemical equation, we'll be able to look at reactants and look at quantities. Like if I have 10 grams of A, how much product would I make? If I were to burn a hydrocarbon with oxygen, if I start off at 10 grams of A hydrocarbon, well, how much carbon dioxide would I make? Okay, things of those calculations, those type of calculations that we eventually will be doing. But we're going to start first with the alphabet, if you will, and introduce you to some physical properties here. So we talked about physical properties. The thing about physical properties is that whatever you do to it, you heat it, you melt it, you boil it, the chemical structure remains the same. That is a chemical change, okay? But the properties such as the melting point, that is the temperature when a solid actually softens and starts to become liquid, or the boiling point when a compound that's a liquid goes into the vapor. Its density that we kind of briefly talked about, which is the ratio of mass over volume. That's a physical property. We all have different we all have different densities. Okay. Solubility, is this material soluble in water or is it soluble in oil-like solvents? Okay. Does it conduct electricity or is it a non-conductor? And even such thing as how hard it is. There are tools that we use to measure the hardness of a particular material. I got a question here. Okay. Is there a problem? Let me check my speaker here. Make sure I'm on the right speaker. Okay. All right. Anybody else having trouble hearing me? Okay, the audio is quite quiet. Okay. All right. You might check on your side of it to make sure it's up to, you got your volume turned up. I did check through. It's just a little quiet. Mason, you got a couple of people there. It's quiet. And so I don't know if it's me. I did check. Let me very quickly check my audio. Make sure speaker, microphone. Okay. Yeah, earphones definitely do help. Okay, Taylor, you can hear me. Let me test my speaker. Okay. Bear with me for a second. I'll make sure. Okay. Testing 1, 2, 3, 4. Testing 1, 2, 3, 4. Let me turn it up here. Okay, I did turn my volume up on my side as far as I can go. So you might, like I say, you might try some earphones. Maybe that might help. I don't know if it's from your end or my end. Yeah, louder. Okay, good. I turned my volume up in Zoom, maxed it out. So hopefully it won't blow anybody's ears out. Okay. Let's go back. All right, so we talked about physical properties, and then there are chemical properties, whether a material is poisonous, it's a chemical property, whether it reacts. There are some material that on contact with water just reacts violently, and I'll talk about one example here when we get a little bit more into chemical reactions. The fact that it rusts, which is a chemical reaction, iron 3 oxide, which we're going to learn about also. All of these are chemical properties. The point about chemical properties is that once they react, they don't go back to whatever chemical structure they had to begin with. You have completely changed the chemical structure. Okay. So physical properties, physical change, no change with respect to the structure. Chemical properties, chemical change, structure completely changes to something else. Okay. Now we have these physical changes and we have specific names of which some of these you're already familiar with. When a solid goes to liquid, we call that melting. Okay. Take a chunk of butter, put it in the pan. What does it do? Hot pan, warms up, and melts. Okay. Nothing scientific about that, right? Okay. But the scientific part comes in that stick of butter they come at room temperature, they're together, held together because of the forces of the molecules of the butter that attract each other. And when we heat it, we break up those forces and hence it liquefies. Okay. Those are called intermolecular forces. We're going to learn, have a whole chapter about that. When the liquid goes to gas, it's either vaporizing, we're evaporating, or it's boiling. Okay. And when a gas goes to a liquid, that's condensation. You see that all the time. You get a nice ice, you make yourself a nice cold drink. Okay, you got a cup sitting there, and then you ice in your cup and whatever liquid you have. And then after a few minutes, what happens to the outside? It condenses, right? Well, where's that water coming from that's on the outside of your glass? Anybody know? You know, was this some Harry Potter stuff that just came in and boom, there it is? Okay. Yeah, where did that water come from that's on the outside of your glass? Anybody know what's going on there? Why you got that water? Exactly. It is, Skylar, it's water from the atmosphere. And it's all related to energy because in the atmosphere around us, obviously Arizona is not that very humid, but if you go back east, you know, Louisiana, I was stationed there for a while. It is humid, huh? Like 1,000% humidity. Okay. And so you have moisture in the atmosphere, water molecules in the vapor phase, full of energy. And that's why they stay in the vapor phase because they get a lot of energy. Now, the moment they hit something that's cold, they lose that energy. They tend to condense, come together. Then those forces that hold molecules together with each other come into play and they change. They go from a gas to a liquid, and hence you have condensation on the outside of your container. Okay, liquid to solid, that we call freezing. Same scenario. We have gas, water molecules in the vapor phase. We reduce the temperature by just reduce the temperature, removes the energy. It goes from a gas to a liquid phase. Okay, we continue to remove the energy, get it colder. The molecules get closer together. They finally go into the solid phase. Okay, we call that freezing. So nothing new here: condensation, melting, boiling, freezing. Now, what might be new is a process that we call solid to gas. Okay, very few molecules do that. You can go to Fry's grocery store and buy yourself some dry ice, because dry ice is nothing more than carbon dioxide. Okay, good old-fashioned carbon dioxide. The thing about carbon dioxide is that it goes directly from the solid to the liquid, basically bypassing solid to the gas, basically bypassing the liquid stage, or being so it goes through it so quick we don't even see it. And we call that sublimation. Okay, when the solid goes direct from solid to gas. Another example would be mothballs. If you ever use mothballs around someplace, this is a chemical called naphthalene, and it also goes directly from solid to a vapor phase, sublimation. Now we can reverse it where we take the gas to solid, and this is one way to make dry ice. If we take carbon dioxide and we convert it back to a solid, and we call that deposition. Okay, so those two probably are the newest terms you may have not known: sublimation and deposition. Okay, and now a physical change, as I stated, a physical change, there is no change to the chemical structure. Now you're going to say, what do you mean the chemical structure, Dr. Fred? Well, this is what we normally do. If we take, for example, water, the formula for water, the way we write it, is we say H2O. Now the subscript here tells us that there are two hydrogens. Okay, and so obviously oxygen has no subscript, so it's assumed, like in mathematics, to be equal to 1. And we can have a variety of different ways, but we write chemical structures. We could have, say, this is called the hydrocarbon. What it is exactly, we don't need to worry about it this time. But the fact is it's made up of nothing but carbon and hydrogen, okay, carbon and hydrogen. The subscript tells us how many of those atoms are involved in this structure, okay? 9 times out of 10, we will tell you what the central atom. In general, what happens with the chemical structures that we're going to be working with, you have one atom that is a central atom, and then everything else is bonded around it. Now, normally, the first atom we write in the formula is the central atom. The only exception is H2O, water. Well, oxygen is the central atom, and these two hydrogens are bonded to the oxygen, okay? But by convention, and that's the way they've been doing it for a long time, they write hydrogen first, then the oxygen. And so if we look at the formula here, we see we have H2O, and then we write the physical state in a letter. L for liquid, G for gas, okay, and S for solid, lowercase. And so we see here, the other aspect to see is we have an arrow. See that arrow sitting there? That arrow tells you there is a process here, be it a physical process or a chemical reaction, okay? And so if you have A and then react, something happens to it, and we go to B, A is the reactant. To the left of the arrow is the reactant. To the right of the arrow are the products. Now, we have this arrow going from left to right, which means it's a one-way road, okay? We will have examples where we have two arrows going the other direction, one going to the right, one going to the left. What that tells you, that's a two-way road, and we have what we call an equilibrium, but more on that later on. So what we've written here is a chemical process or a physical process where we see H2O as a liquid form being converted to H2O in the gas form. And so what we do is we analyze the reaction here. And we see that the structure H2O has not changed. H2O is still the same, whether it is reactant and product. And that should flag for you that it is a physical change, okay? Physical change. Because we will have examples of given these reactions, which at this time you may not know what the structures are or what they are, but analyzing the way the structures are, seeing how many of the atoms we have together, and if they're the same, reacting to product, physical change. On top of that, we will put in the physical state. So that should aid you with respect to whether it's physical or chemical. We'll have some more here in a second about how to describe how a chemical change is described through a chemical process, either a physical process or chemical reaction. Since water is going from liquid to gas, we call that, obviously, that's boiling, okay? That's all it is. Now, the water molecule does not break apart, and that's the important part. The water molecule remains intact as H2O. Nothing has happened to the structure. As compared to a process that, I could take water and I can zap it with some electricity. And guess what? I can break it up into the elements it started off with. That's why it's so important that we find water out in space. Why? Because two things: it gives us oxygen because we need oxygen. And second, it gives us hydrogen gas, which we can use as fuel. But notice the difference here. We start off with H2O, but we end up in the product as two different products, hydrogen and oxygen. So definitely this will be an example of a chemical process, chemical, okay? All right. This diagram just talks about what we just talked about. We're going from solid to gas, called sublimation, from gas to solid deposition, and then notice the one with the double arrows, okay, which is telling you that going from solid to liquid is melting. But if we put energy into the system, okay, Let me draw this. I'm going to designate that as energy. E is energy. If I give it energy plus energy, I break up those molecules. These little spheres represent molecules of something. Okay, and they're hooked up together and they're attracted to each other because of these forces. Well, if I heat it up, or give it some kind of energy, okay, I break up that interaction. I break up that structured, ordered state, and I make it more into a kind of more disorder. They're still combined, but it's a liquid form. They're all kind of moving around. In the solid form, the molecules don't move very much. They still vibrate in place, but they don't move around because they're kind of frozen in space there, if you will. Okay. And if I continue to give it more energy, guess what? I break up that interaction even more. And now I pushed it into the vapor phase. It's about energy. I've not changed the chemical structure here. Okay. These are physical changes here. And when we add energy into the system, okay, we're breaking up that interaction. Now, if we take energy away from the system, those molecules come together because there's less exciting. Anytime you put energy into a system, you excite the molecules. Okay. Think of it as walking, you're 100 plus degrees on the beach in the sand. You got to walk from point A to point B. Walk slow with no barefoot. You'd probably be running a little bit, right? But if it was cool, the temperature's cooler, you'll slow down, right? So you got to eat, put energy into the system, you make things move faster. The converse of that, take energy out, things slow down. And that's what it does in the opposite direction. So I put it down as negative energy. I pull the energy out. And so I start condensing gas to a liquid. And then from there, I freeze it, going back to solid. Okay. Double arrow because I can go in both directions here. Double arrow. And the key point here is I did not change the structure of the molecule, whatever that molecule is. Nothing got changed with respect to the way it is arranged and put together. Okay, more on physical changes. As the stated, molecules are always moving. Even in the solid state, they're frozen in position, but they're still vibrating. It is not until we're going to learn down the road that when you get to what's called absolute zero, which we have not reached that state, we've come close. Only when we get to absolute zero that atoms are supposed to just shut down and do not move anymore. But we haven't been able to attain that order. So even though they're solid, they're moving, they still move. They vibrate, but they're still moving. When you heat ice, like I just stated, you put energy into the system, it gains what we call kinetic energy. And that's a fancy word for energy that makes you move. Kinetic is movement. And yes, the molecules start vibrating a little bit greater. They gain energy even more so. And more energy they gain, the more movement they have till they finally break away from each other and then go into the liquid stage. And if they get enough energy, they will go from solid to liquid, what we just talked about, okay? And then eventually to gas phase. So this diagram kind of demonstrates what we just showed you in the other diagram. Now, the thing about those diagrams, notice here, sometimes you're given a diagram all by itself like this, like the one listed as solid, okay? Or all three of them, solid, liquid, and gas diagram. And you may be asked, which one represents a liquid, okay? Or which diagram represents a gas? And obviously, which one represents a solid material? So these are general diagrams to depict the different stages of physical properties. Okay. All right, chemical change. And now the molecule is broken apart and rearranged to create something else. Okay, this is a chemical change. Now, or AKA chemical reaction. We destroy whatever the starting material is. Okay, the starting material is what is to the left of the reaction arrow. Okay, or the process arrow, because it could be just a physical process. And we create a new substance. For example, we're burning gasoline. I used the example earlier of a hydrocarbon. And here it is again. If you drove your vehicle today, this is what you did. You burnt, or you did a combustion reaction. This is one of the 6 reactions that we will eventually talk about. But that letter there, C and H, 2 elements there, which we're going to learn about these symbols, are nothing more than carbon and hydrogen. X represents a number. And so when you see the X as a subscript, it could be a variety of numbers. But so we give it a general formula. What we burn fuel-wise, gasoline, is nothing but hydrocarbons, and we call it hydrocarbons because they're made up of nothing but carbon and hydrogen. Now, anytime we burn anything, always remember, we need oxygen, obviously, right? Nothing will burn, combust without oxygen. Now, for Chem 130, when we burn a hydrocarbon or combust hydrocarbon, we're only going to define that we get 2 products: carbon dioxide, CO2, and water. Yes, I know that when we burn the vehicle, gasoline will give you carbon monoxide, and that's a side product. And that's mostly because of the inefficiency of our engines and our ability to burn that hydrocarbon properly. So yes, we do get carbon monoxide. But for Chem 130, the only 2 products we'll be getting is carbon dioxide and water. Notice the formulas for carbon dioxide. That means carbon is the central atom. Like I said, normally, other than water, we write it with central atom in the middle. It's front, first one, followed by whatever else is bonded to that carbon. In this case, 2 oxygens are bonded to the carbon. And we're going to learn that structure, that geometry. We're going to learn how to figure that out. Okay. And then we've got H2O. And there's my car that I get next week, right? Yeah. All right. Okay, so indicators of a chemical reaction. Well, how do we know something happened chemically? Okay. Well, there are some indicators we can use. Okay. We can, obviously, if it burns or it rusts. I had an old truck that had a lot of chemical reactions, had a lot of rust on it. Okay. So anytime you release bubbles without any heat, that's a chemical reaction. Good example of this would be Alka-Seltzer. Okay, Alka-Seltzer, which to this day I'm trying to figure out why they put bicarb in the Alka-Seltzer, because then they put a little bit of citric acid, and then what happens when you put it in the water, the citric acid and the bicarb react to form the bubbling, and you get carbon dioxide, and that's what the bubbling's going on. Yeah, but no heat's given off. I don't know what medicinally what the carbon dioxide does. I don't know, but anyway, I've always asked that question, but maybe it's just made up to mix up the liquid. Who knows? So you might get gas bubbles with no heat, not boiling, but just room temperature, ambient temperature bubbling. Or you may get what's called a precipitation reaction. That is, you have 2 liquids that are clear, and you mix them together and boom, you got a solid that occurs. A precipitation reaction. That's a good indication of a reaction. Or you can get something that releases heat or light. Good example of something that releases heat, you go to the pharmacy, you buy a hot pack, you get that little plastic container, you smack it, reaction, the chemicals are interact with each other. During that process, they give off heat. Okay. Or you may have these glowworms or glow sticks, where you take them, you crack them and break the reactions to break the reactant inside that's inside a little glass container. You break it, shake it up a little bit, and you get this glowing light. It's one of the indicators that a reaction preceded. Mixing lye solution, yeah, that wouldn't be a chemical reaction, Skylar. The question is mixing lye with water would be a chemical reaction. Actually, it's a physical reaction because we're going to learn that lye solution is nothing more than what we call sodium hydroxide, which is an ionic compound. And when you take sodium hydroxide and you dissolve it in water, it will give off heat because it's breaking up the two ions and they're breaking up the sodium and the hydroxide. And there's a lot of heat given off and that gets pretty warm. But that would be a physical process. Okay. All right. Reduce heat and light. And then we have color change. You know, two colorless liquids. We put them together. Boom, you get a color change. You know, a good example of that would be if you have a pool, swimming pool at home, you're checking the pH or you're checking the pH of your aquarium. You know, you use an indicator to tell you the color, and that color tells you the pH. That would be a good indication, a good example of color. Or it's an odor that's given out. A lot of the nice smelling odors like winter greens, if you mints and stuff, those are made from a reaction of what we call an acid and an alcohol, which by themselves don't smell that great. But when they combine, they smell pretty good. And then in the other aspect is you get reactions that when they get combined, they smell pretty bad. So odor is a good indication of a chemical reaction. Okay. Now, let's do an example of a chemical reaction. Here we have a chemical reaction between sodium metal and chlorine. Notice it's written out in a sentence. We eventually are going to be able to read that sentence and convert that sentence into a chemical reaction. Write it out, okay? But right now, we're not going to do that right now, but just preparing you, you're going to see a lot of that. Words that say, okay, here's the reaction of sodium. They're telling you the state, it's a solid, and chlorine, which it's stated is a gas. Notice the subscript on Cl, okay? That means there are two chlorines together. We're going to learn that of the 118 elements that we have, 7 of them are what we call diatomic. They require here on Earth, here at ambient temperature, for 2 of them to be together. Okay, by themselves and not stable. Normally, the elements are okay by themselves, the atoms, with the exception of 7 that require them to be together, and hence we call them diatomic. Okay. And we have a little catchphrase to help you out to remember which ones they are. We'll get to that here in a bit. Now, the chemical reaction between sodium metal, which is a solid, and chlorine gas, which is a gas, produces a salt that we're all familiar with. You put that on your French fries, sodium chloride, okay, which is a totally different chemical, okay? Now, sodium metal is a very hazardous metal. You put that in water, it reacts violently. It gives off a lot of heat. It reacts with water to produce hydrogen, and if so much heat is given off that it causes a little bit of an explosion. You might Google sodium, the reactions of sodium. There's YouTube videos of guys out there throwing a big old chunk of sodium into some lake. It's crazy, but it's pretty impressive with respect to the reaction. Now, chlorine gas, which is a gas, it has a yellow tinge to it. Normally, this gas is used in municipalities that treat water for water treatment, because it's good for killing bacteria and all kinds of bad stuff. But it's a poisonous gas. So if you live by a municipality, a water treatment plant, and you ever see a yellowish green cloud coming at you, get up one quickly. They got a gas leak. Okay. Those 2 react. So you got sodium on the left there, and then we got chlorine plus the work to produce sodium chloride, which is a solid. And that is what we can put on French fries. Okay. you don't want to. Sodium chloride is hazardous, of course, because if you have heart trouble, that could be a problem. Too much sodium in your diet's not a good thing. But the thing is here that the only thing we're going to learn here that is one tiny, well, actually 2 electrons were exchanged. Okay, we're going to learn that the elements are made up of 3 subatomic particles: protons, neutrons, and electrons. Now, with respect to weight and mass, the electron is so tiny that we give it a relative mass of 0 compared to the proton and the neutron. We give it a relative mass of 1. But that electrons, that is what all the action about chemistry is about. Without electrons, we wouldn't have what we have, okay, as we know it now. All reactions are up to electrons. And this is one aspect about chemistry that really got me involved with chemistry, because I'm thinking, oh my God, I got this little tiny chunk of mass, and that little chunk of mass, an electron, has such a great factor on the properties of molecules. Okay, just mind-boggling to me. Anyway, there's an example of a chemical reaction. In general, like I said, you have reactants that get broken apart. We have totally different products, totally different products here. All right, so we have a listing of 5 different reactions. So you might think to yourself, oh my God, I don't even know what NH3 is. And that's okay, all right? But so what I want you to do is, when you see this, especially now at this state of Chem 130, is to analyze the reaction and look at the reactants and look at the products. And you can see I have NH3, okay, which nitrogen being first tells me that nitrogen is the central atom. And these 3 hydrogens, remember the subscript tells me there's 3 hydrogens, are bonded around the nitrogen. Okay, we got that. Plus, it's in the gas stage, okay? But then we move over to the product side. And again, guess what? We got the same structure, the same formula, NH3, okay? And then the difference between the two is that here, the physical state is now a liquid. So point 1, the structure has not changed from reactant to product. It's still NH3. And the only difference is the physical state. So that indicates that we have a physical change, okay? All right. Now, if we look at the next number 2, again, we have NH3, but this time, the key thing that I see, I got a plus in this reaction. And that plus tells me I got products here. I got 2 different products, because I have on one side of that plus, I have N2, which, by the way, is another of those diatomic elements I talked about. Chlorine was one of them. Nitrogen is another one. All we got to do is learn 5 more, okay? And then let me give you another diatomic element, H2. So guess what? Now you learn 3 of the 7 diatomic elements. We've learned chlorine, nitrogen, and hydrogen. So all we got to deal with is 4 more, and we'll get to that. So you can see here that NH3, which, by the way, is something you're familiar with. You may find it with window cleaner, or if you have a baby at home and you got diapers hanging around, you know what NH3 is. That is the formula for ammonia. Okay, ammonia, NH3, FYI. It'll be coming back to us. We'll be using ammonia quite a bit in examples here with respect to structure and so forth. All right, so number 2 would be a chemical change, because we broke up NH3 into 2 different components, in this case, nitrogen and hydrogen. All right, now let's take a look at number 3. All right, you might think at first glance, I got water here, H2O. However, look at it a little closer. there's a subscript 2 in oxygen. So we really have H2O2, which is not water, okay? Which is not water. But it's a liquid, and I'll tell you what that is. And something happens to it, and guess what? I got another plus symbol here, which again is a flag to tell me I got a chemical reaction occurring here, not physical. And what I have made is the diatomic element hydrogen, H2, and here's another diatomic element, something that we all need, oxygen, O2, alpha gas. So now you know chlorine, nitrogen, hydrogen, and oxygen. You got 4 of the 7 diatomic elements. Okay. All right, let's look at, well, before I leave this, you might think, that's H2O, which we know is water, versus H2O2. And I'm very sure that you are familiar with H2O2 because it has, if you ever cut your finger, you put some liquid on that, or if you ever use it to kind of blow your hair up a little bit. How about peroxide, hydrogen peroxide? That is the formula for hydrogen peroxide, by the way. Okay. Number 4, we start again with hydrogen peroxide again, H2O2, it's a liquid. And then the product remains the same, H2O2. So right there, it tells you I got a physical change because I didn't do anything to the chemical. Still intact as H2O2. The only thing difference is it starts as a liquid, goes to a solid. Okay, liquid to solid, we call that freezing, right? And so it remains. Excuse me. It remains the same physical change. Okay, number 5. Number 5. Okay, again, you don't know what that is, but we analyze it. We got C6H6. That means there's 6 carbons and 6 hydrogens, and as a reactant. And then on the product side, guess what? It remains the same, C6H6. Again, we got a physical change because we're going from liquid to gas. That sounds like boiling to me, right? Liquid to gas. And that, it has a specific name. It's called benzene. It's not important. It's a cancer-causing compound. But we call it, in general terms, a hydrocarbon because it's made up of nothing but hydrogen and carbon. I would mention that because benzene has been shown to cause cancer, and there's a lot of old transformers out there that break the electricity down to a voltage that's usable by the house. But these old transformers, the old ones, still had a lot of liquids inside, hydrocarbons, and they contained a lot of benzene. I don't know if they're still out there, but they were when I was growing up. So anyway, stay away from transformers, basically. All right, so let me clear this up here. And so we got physical, chemical change, where the first one, physical, ammonia going to ammonia, gas to liquid. The number 2, ammonia got broken down to its elements, okay? Now, number 2 represents another type of reaction called decomposition. We talked about combustion reaction. I talked to you about an acid-base reaction when you take Tums to kind of reduce the acid. And so now you have another example of the 6 types of reactions of decomposition because ammonia, number 2, it decomposed into these elements. Okay, so is number 3 is also a chemical, also a decomposition. And number 4, as we talked about, is a physical change. Nothing happened to the structure. And number 5 also is a physical change because nothing happened to the structure. Only the physical state changed. Okay, So these are typical types of reactions that you may see in the homework or exams. And even though you may not know what the structure is and what it is chemically, analyze product and reactant. Okay, look at it. If it looks the same, like number one, ammonia NH3 still is NH3 at the other end of the arrow, then that's just simply an indication of a physical change. You see that plus sign on the reactant product side? That's a good indication that you're dealing with a chemical change. Okay. All right, so it brings us to elements, compounds, and mixtures. Now, elements, there's 118 elements, of which if hopefully you downloaded and printed out that periodic table, it lists all of the elements known to date. They are working on more, but they haven't been able to make them. Okay, and they're getting there. Now it's one type. An element is one type of atom only. It can be a single element, or like I stated earlier, it could be a diatomic, simply because by themselves they're not very stable here on our conditions. Now, when we talk about physical state, we're talking about what's happening here on Earth. Because obviously, if all these elements were on the surface of the sun, we're all going to be gas, right? So we always got to talk about a reference point. And so when we talk about physical state, we're talking about here on Earth, conditions here on Earth, nothing fancy. Okay. The element cannot be broken down any further. It is what it is. If we break it down further, then it is starting to break it down into the subatomic particles. And that's no longer the element. Is subatomic particles are what the element is made up of. With respect to compounds, that is when two or more different elements, okay, or atoms are bonded together, okay? And they can be broken down to the elements. The case example we just did was NH3, ammonia. NH3 is two different elements bonded together. And that example in the previous slide that we was broken down, it got broken down to nitrogen and hydrogen, okay? So compounds can be broken down to the elements, to the atoms themselves, that's it. And the elements, that's where they stop. We can't break those down any further unless we start breaking down the particles of what they're made up of. All right. What amazes me about this whole chemistry thing, I think of it as like Legos. You know, you got Legos, you can have Legos of same size, same shape, and you can make an infinite number of structures. And the subatomic particles to me are Legos. And when you're put together and you think, hey, one thing can make at least 118 different elements. And then those guys can get together to make just millions of different compounds. It's just pretty cool, I think. Now, obviously, something that's pure, self-explanatory, you know, all the particles and whatever something's pure are the same, okay? You can't separate them anymore. They're pure. And obviously something that has two or more different particles, whatever they may be, they could be compounds, they could be elements, any combination, you know, it's a mixture, you know, stands to reason, pretty self-explanatory. Explanatory. One of those words. I'm having trouble this morning. Not enough coffee yet. Okay, so here we have these diagrams. Down at the bottom, these spheres, the spheres represent either elements. If they are the same color and they're single, that's a good indication of an element. If they're put together and bonded together in the same color, that is a good indication of, let me show you here. Pretty good. Okay. You know, if we look at these, we can see there's two cut red spheres. They're diatomic, same shape, That's a good indication of a diatomic compound. Okay. These red ones here are all separated, all by themselves, but they're all the same color. That's a good indication of an element. Okay. Now, if you look at this, looks like Mickey Mouse looking at you, right? Two yellow ears popping up there and the red face in the middle. Well, that's a good indication of a compound because you got two different colors, indicates two different elements. By definition, a compound consists of two different elements. Okay. And here again, we have a compound, two different colors combined, kind of attached to each other. Okay. And then over here, if we look to the right side, on the right side, and I'm just looking at the diagram right now, we have looks like a diatomic element. And then we have the dark spheres all by themselves. And very similar to this diagram, we got that color, the magenta, I guess you call it, green, the black, and the red. You know, all this is a mixture. It looks like a bunch of NMMs in there, right? Different colors. We get a mixture in there. And on the left, occasionally you get an NMM that is a double, right? That's a good analogy for the left side there in mixture. So what we do is we look at matter, and if it's a mixture, we're going out in this direction, pretty self-explanatory. Okay, these diagrams represent a mixture. Okay, when we get to pure substance, that's in the other side of the flow chart, it's going to be one or two things. It's going to be either a compound, which we know by definition is made up of two or more different elements. And if you look at these two structures down here, here and here, they're combined with two or more different elements. So they're compounds. Down here, the elements, if they're single element themselves, are simply called atoms. Atoms of whatever, carbon, atoms of helium, atoms or whatever. If they're diatomic, a good example of HO2, then they use the term molecule. So you have a molecule of oxygen, a molecule of hydrogen, just for the diatomic. Okay. So this flow chart, I think, is pretty self-explanatory. Okay, some examples of mixtures. For example, we may not think of it, but a lot of metal alloys, the gold that we have, 18 karat gold, brass, steel, those are mixtures because normally steel, as we know, is iron, but pure iron by itself is not very strong. So other components are added to them, hence making a mixture to give it the strength. Brass is made up of copper and zinc, for example. And then we got 18 karat gold and so forth. The pure gold is very soft metal, very soft. It'd be tough for it to be jewelry and withstand the pressures of everyday use on your ring, on your hand. You know, it'll get smashed. Tap water, why is tap water a mixture? Because what's coming out of your tap water has a lot of stuff, a lot of ions, and there are a bunch of other things in there. Okay. The air around us is a mixture. It's made up of nitrogen, oxygen, all kinds of gases. So here's some examples of mixtures. Pure material, okay. Salt, sodium chloride, pure material, okay. In the solid form, pure. Obviously, if you dissolve it in water, it's no longer it's a mixture because now you got water and sodium chloride. But sodium chloride solid is a pure material. If you purify it, let me clarify that. Yes, you can make sodium chloride and get it ready, and it's a little bit dirty, but you have to go through the process to get it clean. So we're talking about processed sodium chloride. It's like sugar. Sugar itself needs to be processed to be cleaned up. A diamond. Very rare do you get one that's 100% carbon and pure, but if you do, that's a pure material. Distilled water is an example of something that's pure. Distilled meaning that you take water and you boil it, and you have a special unit that you condense it, and then collect the water vapor, recondense and collect the new liquid. By boiling it, you send it up to the vapor phase and leaves all the junk in the container. A good example of this is a good old fashioned moonshine. You ever see that show on moonshiners on TV where they're making the still, where they're purifying their alcohol? Okay. And some metals are pure. So again, diagrams, we use those a lot. You can see in the far left, we have an example of an element, okay? And we say that because, first of all, the shape, the size are the same, and they're same color, and there's two of them bonded together. So that's a good example of a diatomic, a molecule of a diatomic element, okay? And the one in the middle, you got the white sphere is in the center, and the dark ones are bonded around it. It could be any multiple different compounds, but we got two or more different elements, and therefore this is an example of a compound. And then we have a mixture. In here we got good old Mickey Mouse ears again. Okay, so we have a mixture of compound and two different elements. Okay, two different elements designated by, here's one and here's one. Okay, these two are the same in white cells, and then these are the compounds. All right, so you may have a table where you say, okay, is this a compound, element, or mixture? So if we look at A, again, diatomic spheres, the round spheres are clear, the same shape, same size. Whoa, that's an indication of an element. B would be a compound, okay? C would be a mixture of two different elements, okay? Two different elements. You get the white one and the dark one there, okay? D, again, would be a pure material of an element. That's all it is, just the single dark sphere. If there was one that was bigger in there, larger size than dark, that's probably a mixture then, but not, they're all the same relative size. E would be a compound, indicates a compound because we got two different elements bonded together. And F definitely would be a mixture of an element and a compound, specifically a diatomic element right here, and two different compounds. G would be a mixture, okay, of element again and a compound. And obviously H, you can see it's an element, and more importantly, you can see how structured it is. So I could also even conclude that H could represent a solid, something, a pure solid. The others, they're all moving around. It could be a liquid, could be a gas, but definitely not a solid. Okay. What time? Give me about 10 more minutes and we'll take a quick break. You guys give you a break here. All right, let's talk about elements. Each element has a unique name, okay? And it has a unique symbol and a unique number. There's 118 elements. Each one has a number. So let me pull up that periodic table real quick. Where's it at? Where'd it go? Oh, okay. So it's hiding from me. Okay, so here we got the periodic table. Now, this is the one that we utilize. Now, I know you might be tempted to look up information for the elements, but my suggestion is use the information from our periodic table. The reason I state that is when we get ready to do calculations, there's a number. If you look carefully, there is a number. And I put the periodic table down a bit closer so I can see. Now zoom in. Here's a periodic table and the symbols. Either the symbols will be a single letter or a double letter. So if you look at hydrogen up here on the far left, number 1, there's that number it has. Okay, hydrogen. Its number is 1, and underneath the symbol has a decimal number. That is what we call a atomic weight. Every one of these has a decimal number underneath its symbol. Okay, that number has an infinite number of numbers, if that makes sense. And will make more sense here when we talk about significant figures. And so if you look up that atomic weight for any of these elements, you're going to end up with numbers that are like, 100 digits long. Okay. And then when you do your calculations, it might be off a little bit. Okay. Tell you what, let's take a quick break. Okay. And I'll be back in a few minutes. And we'll come back, let's come back at 2:15. Okay. 2:15.